Today we are going to be focusing on how to graph exponential graphs and some application problems with exponential functions. So first of all, I'm going to show you the equation for an exponential graph. So an exponential is y equals a. So a is usually our starting point if we don't have a vertical shift, times our b value. B value is going to be very important, raised to the x plus k. So the two main things we need to focus on are our b value and our k value. So first of all, our b value, if our b value is greater than 1, we have an exponential growth problem. Okay, and your curve will go up. If our b value is between 0 and 1, we have an exponential decay problem, and your graph will curve down and to the right. The other thing we see here is we have a y equals k, or an asymptote. So an asymptote, you might remember, is where the graph can't exist. So here you can see I have a horizontal asymptote. This one happens to be at 0. So that would be if our graph did not have a k value. This one, we have it down here lower, so our k value is something less than 1, and our graph curves down and never touches that. So first we're going to practice evaluating some functions. So to evaluate a function is pretty simple. So here it says h of x equals 10 times 1/5 to the x plus 2, and we need to find h of 0. So remember, if we're finding h of 0, all we're doing is we're replacing our x value with 0. So in this problem, h of 0 is equal to 10 times 1/5 raised to the 0 plus 2. So you may recall, anytime you're taking a value and you're raising it to the 0, it's simply 1. So then all we do is we have 10 times 1 plus 2, which leaves us with our h of 0 equaling 12. In our second problem, we have g of x is equal to 2 times 6 to the x plus 3. And it wants us to find g of 3. So that means I'm replacing my x with a 3. So g of 3 is equal to 2 times 6 cubed plus 3. So let's make sure you know how to do this in Desmos. Okay, so we have 2 parentheses 6. When you want to raise it to a power, you hit the a to the b button to the third. Then make sure you go outside your parentheses here and minus 2. No, just kidding, this one wasn't minus 2, plus 3. And we get 435, which is what we see right here. You could have also in your head gone 6 cubed. Just make sure you do the power first. So 6 times 6 times 6 gives us our 216, and 2 times 216 plus 3 is 435. Now we're going to graph some functions. So for number 3, I have f of x is equal to 1/3 to the x minus 2. There's a few ways to graph. The easiest is to use a table like we're doing here. First thing I like to look at is I like to see if I have or where my asymptote is. So I have to find the k value in my equation. So right here, I'm subtracting 2 at the end. So that means I have an asymptote at y equals -2. So if I go over my graph, I go down to -2, and I make myself my horizontal asymptote. Okay, now we need to plug in values. So you can plug in any values you want. Here in the worksheet, it will give you which values to plug in for x. So first I'm going to plug in -1. So you might recall that when we plug in a negative, it makes whatever you have flip over. Let's go ahead and do it in Desmos just to make sure you know. So 1/3 in parentheses, so 1 divided by 3. Arrow over before you raise it to your power. So we're raising it to the -1. Arrow outside your parentheses, and minus 2. And we get 1. And that's what you can see here. When I plugged in -1, I got +1. So go ahead, go over my graph, -1 to the right, up 1, and I have my first point. My second point, I can just keep using that same equation in Desmos and just plug in 0 instead of that -1. So just come over here and delete that and put in 0. And we can see our answer is -1. So I add 0 and negative 1. So go to my graph, 0, negative 1. And lastly, I can use that same equation in Desmos and now just plug in 1. Arrow over, delete that, and plug in 1. And we have negative 1.66. If you want to change that to a fraction, you can use this vertical column that's blue over here, and it's negative 5/3. Oops. And so our third point is 1 and negative 5/3. So we go over here, 1. Negative 5/3 is between negative 1 and negative 2. So I put my dot here, and I sketch in my curve, making sure it keeps going forever to the right but never touches that asymptote. For our next problem here, we have h of x is equal to 2 times 3 raised to the x plus 1. So again, I like to start with my asymptote. What am I adding on the end? 1. So I know I have a horizontal asymptote at y equals 1. So over here on my graph, here's where y is 1. Make your horizontal dashed line. Your graph can never touch. Okay, we're going to be plugging in negative 1, 0, and 1 again. So 2 times 3 to the negative 1 plus 1. So 2 times 3 raised to the negative 1 plus 1. And I get 5/3. And you can see we have that for our first point here, negative 1 and 5/3. So 5/3 is again between positive 1 and positive 2. So if I go over here to negative 1, and I go up just almost to positive 2 and put my point. Next, I have 2 times 3 to the 0. So let's just try to do this one in our head. 3 to the 0, remember anything raised to the 0 is 1. So I have 2 times 1, which is 2, and 2 plus 1 is 3. So I plot the point 0, up, 1, 2, oh, should be a little bit higher, 3. Okay, now we can go ahead and go back to 3 to the first. Well, 3 to the first we know is 3. 3 times 2 is 6, and 6 plus 1 is 7. So our last dot is at 1 and 7. So over here at 1, 1, 2, 3, 4, 5, 6. Oops, touched too early. Oh, good, got rid of my other dot. Well, we remember where it was. And then we just go through and sketch our exponential growth problem. You can always check if you've done it right. Here, remember, growth is supposed to look like it's curving up, which it is, and our b value is 3, which is greater than 1. And let's do one more. So g of x is equal to 4 raised to the x. So do I have a k value on this one? No, there's nothing being added or subtracted. So that means my asymptote is at y equals 0. Right here on the x-axis. Okay, now I've plugged in a few extra points here. No big deal why. So we have 4 raised to the negative 1 first. So remember, anytime something's raised to the negative 1, it flips it over. So this is really 4 over 1. So 4 over 1 flipped over becomes 1/4. Negative 1 and 1/4. Negative 1 and 1/4. Now when we plug into the 0, remember anything raised to the 0 power is just 1. So 4 to the 0 is just 1. So I plot 0 and 1. Now if I plug in 1, 4 to the first, well, 4 to the first is just 4. So I plot 1 and 4. Okay, and just one more, just in case. We've got 4 squared, and 4 squared we know is 16. So of course my graph is going to continue up, but I don't need to worry about plotting that point if I don't want to. And another exponential growth problem. Now on the next page, we're going to do some application problems. Oops, just kidding. Okay, so for these exponential growth application problems, we have to look at two things. So first of all, we have an a value. So the a value is going to be your initial value, so that's going to be important. It's going to deal with like how much money you started with or how much money you had to pay first. or how much something was worth. Your rate is also very important. This is your rate of increase or decrease. So in these problems, they're going to give you percentages. They're going to give you like 10% or 20% or 6%. You don't just plug that in though. So if it's an increase and if it's going up, you change whatever your percentage is to a decimal, remember by moving it over 2, and then adding 1. So if it's an increase, change your percent to a decimal and then add 1. If it's a decrease instead, you're going to take 1 minus whatever your percent was changed to a decimal. So I will go over that. So here you have invested $5,000 in a bank account with an interest rate of 8%. Write a function to represent this situation. So first we have to deal with our initial value. What's our initial value? $5,000. So that goes in for A. So h of x or k of x or f of x, whatever you want to call it, is equal to $5,000. Times our rate. So is this a rate of increase or decrease? We're investing money, so we better darn hope that we're increasing our money, right? Okay, so for our increase, we change our percent to our decimal. So 8%, change to a decimal, move it over 2, 0.08, and then take 0.08 plus 1. So you get 1.08, and that's what we plug in here. So our function is 5,000 times 1.08 raised to the x. For the next part of the problem, it says, how much is in the account after 20 years? So 20 years is our x value. There are more complicated types of problems with investments, whether it's compounded annually or monthly, but we're just doing simple ones right here. So all we do is we take that $5,000 that we had, times our rate of 1.08, and we raise it to the 20, because we're dealing with 20 years. So let's go ahead and do that in decimals. So we had $5,000 times 1.08 raised to the 20th. And we have our answer of $23,304.79. And that is what we have right here. Now for the third part of our problem, part C, how long will it take to earn $30,000? So we are basically going to be guessing and checking. We'll teach you later on in the unit how to do it using logs. So for right now, we want to earn $30,000. So that's our total. That's our h of x. So 30,000 is equal to our initial investment of 5,000 times our 1.08, which is the same, raised to the x. So we're trying to solve for this exponent variable. So you can just plug in and keep going until you get it, but it does help to isolate your 1.08 first. And the easiest way to do that is to divide both sides by 5,000. So if you divide both sides by 5,000, we get 30,000 divided by 5,000, which is 6, is equal to our 1.08 to the x. So we're going to go on to decimals here. We know that in 20 years, we have 23,000. So we want 30,000. So it's going to have to be a value larger than 20. So I'm going to just keep going into decimals until I get at least 6. So 1.08 raised to what will give us 6? So here we go, 1.08. So we know it has to be larger than 20. So raised to the, let's go 22. 5.4, not quite. Delete that to the 23rd. 5.8, closer. 24. There we go, we're over 6. So we need to be investing for at least 24 years. And that's what we can see is our answer right here. Okay, and let's go through one more problem here. Here we purchased a car for $30,000 and it depreciates 10% a year. So anytime you get a car, the second you drive it off the lot, loses quite a bit of money right away. Only certain classic cars, of course, increase or appreciate and earn money over time. So depreciating. So that means that it's decreasing. So to decrease 10% a year, we're going to do 1 minus our percent changed to a decimal. So our percent was 10%. 10%, when you move that decimal over 2, right, 1, 2, it becomes 0.1. Or if you think about money, 10 cents is 0.1. So 1 minus 0.1 leaves us with 0.9 is our R value. Sorry. So we need to go ahead and write our function. So we purchased it for $30,000. Purchase price of our car, $30,000. Depreciating, our rate we now have is 0.90 raised to the x. Now, how much will it be worth in 6 years? 6 years is our x value we're going to plug in. 6 years, 6 years. So we're going to plug in 30,000 times 0.9 raised to the 6th. 30,000, parentheses, 0.9 raised to the 6th. And there, it's almost half its value already. So $15,943.23. In only 6 years. So how long will it take for it to equal almost nothing? Okay, so we want it to equal as close to 0 as possible. You obviously want to sell it, get as many miles out of it as you can, or just use it for a really long time, right? So equal almost nothing. So 30,000 times 0.9 raised to the x. So we want it to equal 0. So basically, if we divided 0 by anything, you're going to have 0. So in Desmos, we're just going to keep hitting 0.9 raised to the x until it's 50 years. This is kind of a silly problem because cars usually don't equal nothing unless they don't run anymore. So 0.9 raised to what will give us 0? So 0.9 raised to the, let's try 20. Oh, pretty close. 0.9, oops. Let's go 30. Closer. So this is kind of a hard one because how close to nothing do we want? It's closer to nothing, but 50. Okay, so there we're technically at 0.1 cents. So for this problem, that's acceptable. Obviously, if you wanted to be a perfectionist, you could keep going and get it to be really 0. So it doesn't really matter anything around 50 or up. We won't give you one that's that arbitrary on the test. So here, again, I said approximate 50 years, but anything greater than 50 would be fine as well. And that is all for today.